Next time you walk under a bridge or step into an elevator, stop for a second. Everything above your head, the concrete, the glass, even the air you breathe, is hanging by something you never notice: steel cables. But what if I told you those cables begin their life deep underground, inside roaring mines of molten rock? Stay with me. By the end of this video, you'll never look at a bridge the same way again. And if you love seeing how the modern world is actually built, hit subscribe to Assembly Forge. Step 1. The hidden beginning. Every steel cable begins its life not in a factory, but in the belly of the earth. Deep mines across the world, some descending hundreds of meters below ground, are where the journey starts. Here, colossal drills bite into solid rock, creating holes big enough for controlled explosions. With a thunderous crack, the rock fractures, freeing chunks of reddish-brown iron ore. At the processing yard, that raw ore is dumped into massive hoppers. Conveyor belts, some stretching for hundreds of meters, carry the material to vibrating screens that shake loose dirt and debris. Step 2. The journey to the steel mill. From rock to metal. Once refined, the iron ore is shipped by train, barge, or cargo vessel to massive steel plants. Each shipment contains thousands of tons, feeding the insatiable appetite of furnaces that never sleep. Here, the iron ore is mixed with recycled scrap metal and other alloys, then fed into enormous electric arc furnaces. These giants generate enough heat, over 2,900 degrees Fahrenheit, to melt solid rock into a liquid that glows like the surface of a volcano. It's not just about melting metal, it's about crafting a perfect balance of chemistry. Sensors embedded around the furnace constantly monitor composition and temperature. Every second matters. If the balance shifts even slightly, the metal's entire structure could be compromised. It's a dance between science and fire, a controlled chaos that transforms the Earth's raw elements into one of humanity's strongest materials. Step 3. Casting strength. From liquid fire to solid form. Once the molten steel is perfected, it's time to give it shape. The liquid is poured through special copper molds in a process called continuous casting. These molds are cooled by powerful water jets, freezing the steel's outer layer in seconds while the inside remains molten. Slowly, the metal solidifies from the outside in, emerging as long, glowing billets, thick rectangular blocks several meters in length. Each billet moves directly from casting to rolling while it's still red hot, wasting no time and no heat. Step 4. The science of strength. Hot rolling and cooling. Once shaped, the steel is still glowing, hotter than lava. It's cooled in a carefully controlled process using high-pressure water jets that hiss and steam on contact. The goal is not just to lower temperature, it's to fine-tune the steel's microscopic structure. Too fast, and the metal becomes brittle. Too slow, and it stays too soft. After cooling, the bars are checked for consistency and microcracks. Advanced sensors and ultrasonic scanners probe deep inside, searching for hidden weaknesses. Only the pieces. Step 5. Preparing for precision. Now that the steel has been shaped and cooled, it's time to prepare for its next test: becoming wire. The long, uniform rods are loaded into massive spooling systems, then fed into machines that will stretch them thinner and thinner. Imagine pulling a metal thread through a series of microscopic rings, each one narrower than the last. That's what happens next, but on an industrial scale. The transformation is nothing short of miraculous. These thick rods will be reduced to wires thinner than your pinky, yet exponentially stronger. The process demands both brute force and delicate balance. Too much tension and the wire snaps. Too little and it fails to form properly. To maintain this balance, the machinery runs under constant digital supervision, making real-time adjustments down to fractions of a millimeter. Before the drawing begins, each rod is coated in a fine layer of lubricant to reduce friction and prevent microscopic damage. It's the first step in turning molten metal into a masterpiece of engineering, one strand at a time. Step 6. Drawing the steel. From rods to hair-thin power. Now that the steel rods have cooled and passed inspection, it's time for one of the most mesmerizing steps in the process: wire drawing. Each glowing bar is first cut into manageable lengths, coiled, and then fed into an enormous drawing machine. Here's where the real magic happens. The steel is pulled through a series of tungsten carbide dies, tiny openings that gradually shrink in diameter. With each pass, the wire becomes thinner, longer and smoother. Imagine pulling a 2-inch thick rod through dozens of polished steel rings until it's just a few millimeters across, all without breaking. The tension, the speed, and even the temperature have to be controlled to microscopic precision. As the wire stretches, its internal structure changes. The metal's grains realign, becoming denser and stronger. This is what gives steel cables their almost supernatural toughness, the ability to bend and flex under immense loads without snapping. Throughout the process, laser scanners continuously measure the diameter of each wire. If a single micron drifts off spec, the system automatically adjusts pulling force and die pressure to correct it. It's a dance of mechanics and mathematics, industrial choreography at its finest. Step 7. Heat treatment, strength forged in fire. But drawing alone isn't enough. The wire, though strong, is now too rigid and brittle to twist or bend. To fix that, it must be reheated and restructured in an industrial process called annealing. The coils are unrolled and passed through long furnaces where the temperature soars above 1,000 degrees Fahrenheit. Once the right temperature is reached, the wire is rapidly cooled using high-pressure air or oil in a process known as quenching. This sudden drop in temperature locks in the new structure, creating an ideal balance of strength and ductility. The sound inside this part of the plant is surreal, a mix of hissing air, roaring furnaces, and the steady hum of conveyor lines moving miles of glowing steel. By the time the coils emerge, they've transformed again. No longer raw metal, but precision-engineered filaments of strength. Step 8. Coating for corrosion resistance. Even the toughest steel would rust away without protection. That's why the next stage focuses on coating and surface treatment, a vital defense against time, water, and corrosion. Each strand of wire is cleaned first using acid baths that strip away oil, dirt, and microscopic oxidation. Then comes the protective coating, typically zinc galvanization or polymer layering, depending on the cable's final use. In galvanizing, the wire is dipped into a bath of molten zinc, which fuses to the surface and forms a metallic armor. For cables destined for marine or industrial environments, additional polymer coatings, often in silver gray or black, add another layer of defense against salt, moisture, and chemical exposure. Every millimeter of coating is inspected. Cameras scan continuously for inconsistencies, and sensors detect any uneven thickness. Even a single air bubble trapped beneath the surface can weaken a wire meant to hold hundreds of tons. This stage ensures longevity. Step 9. Testing the limits, inspection and quality control. Once coated, every wire faces its moment of truth. In the inspection hall, advanced equipment checks each coil against precise specifications. The diameter must be exact down to thousandths of an inch, and the surface must be flawless. No bends, no scratches, no microscopic cracks. Some tests are non-destructive, using ultrasonic waves to look deep inside the wire for hidden voids or weaknesses. Others are brutal. Tensile machines stretch samples until they finally snap, revealing their breaking strength. Every coil is tracked with a digital ID that records its entire production history, from the batch of ore it came from to the specific furnace that melted it. If one fails a test, it's immediately quarantined and melted down again. Only the best make it forward. To the untrained eye, these inspections might seem extreme, but in real-world applications, a single weak wire could mean disaster. That's why the standards here are absolute. Precision isn't optional, it's survival. Step 10. Spooling the steel. With all inspections complete, the wires are finally coiled and readied for the next phase, stranding. Massive automated spooling systems wind each wire into perfect loops, layer by layer, under constant tension control. Sensors monitor the pressure and alignment so that every turn sits flawlessly. If one coil is too tight, it can deform the wire. If too loose, it tangles. The result is a neatly wound, shimmering roll of steel that looks deceptively delicate, but each one contains enough wire to stretch over several miles. Before being sent to the next building, the coils are tagged and sealed, protected from dust and humidity. Some are wrapped in heat shrink film, others stored in oilcloth for long-term preservation. Here, inside these giant coils, lies the foundation of the modern world. Countless strands of metal, waiting to be woven into the cables that suspend our cities in the sky. Step 11, the stranding line. After miles of fine wire have been drawn, tested, and coated, they arrive at the most hypnotic part of the production line, the stranding hall. This enormous section of the factory is filled with the low, rhythmic hum of motors, spinning drums, and flashing lights. Here, hundreds of individual wire spools are mounted onto huge rotating cages that can stretch the length of a football field. Each cage spins in perfect synchronization around a central axis, twisting dozens of wires together as they feed toward the far end of the line. The process looks simple, like braiding hair made of steel, but the precision is astounding. Before production begins, engineers calculate the twist pitch, or how many rotations per meter the machine must make to achieve the required flexibility and load capacity. A smaller pitch gives greater strength, but less flexibility, while a wider pitch makes the cable easier to bend but slightly weaker. During operation, sensors constantly measure tension, vibration, and alignment. If one wire tightens even slightly more than the rest, it could compromise the cable's balance. The system immediately corrects itself, ensuring every strand contributes equally to the final structure. From above, the machine looks like a colossal silver snake slithering across the factory floor, a continuous helix of steel extending for hundreds of meters. By the time it emerges from the other end, the once independent wires have become a single unified strand, the backbone of the world's bridges, cranes, elevators, and suspension systems. Step 12. Core construction. At the center of every steel cable lies its core, the part that defines how it behaves under pressure. This core can be made of different materials depending on where the cable will serve. For high-tensile structures like suspension bridges or skyscraper elevators, the core is made of steel wire, giving it unmatched compressive strength. But for marine, mining, or offshore rigs where corrosion is relentless, manufacturers often use polypropylene or natural fiber cores, which are lighter and naturally resistant to moisture. Before stranding begins, the core is pre-tensioned on its own reel. As the rotating cages twist the surrounding wires into place, the core travels steadily along the center line, maintaining perfect alignment. Engineers call this lay control, keeping each layer in balance so the finished cable doesn't twist, unwind, or kink under load. Layer by layer, additional strands are wound around the core, each one interlocking with the previous layer like threads in a giant steel fabric. The first layer provides strength, the next adds stability, and the outermost layer gives protection against abrasion and environmental stress. By the time all layers are complete, the finished cable can contain hundreds of individual wires, each one thinner than a pencil, but collectively capable of holding hundreds of tons. It's a fusion of micro-precision and macro-scale, an engineered masterpiece that looks deceptively simple on the surface. Step 13. Controlled power. Making a 10,000-foot-long cable isn't just about twisting wires. It's about controlling the massive forces involved. Each rotating cage weighs several tons, and the torque generated by these machines is immense. Modern stranding systems rely on digital synchronization between multiple motors. Every cage, feeder, and tensioner is linked through a centralized control network that maintains rotational accuracy down to fractions of a degree. The larger the cable, the slower the rotation. Any faster and the internal friction could generate heat that weakens the steel. High-speed cameras positioned along the line feed live data to engineers in control booths, who monitor every strand through digital displays. One misalignment could mean hours of rework, so vigilance is constant. Every foot of cable represents not just material, but meticulous coordination between mechanics, computers, and human expertise. By the time the cable exits the stranding hall, it's already several inches thick and stretches continuously across the production floor, a shimmering metallic serpent coiled with potential energy. Step 14. The final armor. Even after perfect stranding, the cable isn't ready to face the elements. Without proper lubrication, internal friction between wires can slowly eat away at the structure during bending or vibration. That's where the lubrication line comes in, the final layer of protection. The massive cable is slowly pulled through a pressurized chamber where high-grade industrial lubricants are sprayed from every angle. The temperature and viscosity of the oil are carefully regulated so it can seep deep into the smallest grooves between the twisted wires. Some cables use synthetic oils with antioxidation additives. Others are treated with specialized greases containing corrosion inhibitors and water-repelling compounds. For cables destined for marine use, such as deep-sea mooring lines, extra compounds are added to prevent electrochemical corrosion from saltwater exposure. Flow meters, temperature gauges, and pressure sensors make sure the application is perfectly uniform. Too much oil can cause slippage. Too little leaves the steel unprotected. It's a delicate balance that ensures the cable can flex, twist, and endure decades of constant movement without internal wear. As the cable exits the lubrication chamber, it gleams with a smooth, slightly glossy finish, ready to resist rust, water, and time itself. Step 15, the endless coil. The final act of the production process is one of scale and precision. The finished cable, sometimes stretching more than 10,000 feet in length, must be coiled without damaging its structure. This happens on a massive rotating turntable that slowly spins as the cable is fed onto it. A computer-controlled guide arm moves side to side, laying each layer perfectly flat. Tension sensors continuously adjust pulling force to prevent any slack or compression. The coil grows, turn after turn, until it weighs tens of tons. Once the entire length is wound, hydraulic clamps secure the ends, and technicians attach ID tags containing all production data, including steel composition, coating type, and tensile strength records. Finally, the entire coil is wrapped in moisture-resistant film and sealed for shipping. Automated cranes are lifted onto heavy-duty pallets, and from there, forklifts transport it to storage bays where it awaits shipment. Some coils are destined for bridge construction, others for elevator systems, offshore rigs, or massive suspension cranes. Step 16, the trial by force. Before any steel cable leaves the factory floor, it must face the most demanding test of its life, the tensiles trial. This is where engineering theory meets brute reality. In a hall lined with hydraulic testing rigs, each as long as a bus, cables are clamped into massive steel jaws. Hydraulic pistons apply tension that slowly climbs, hundreds, then thousands of pounds of force. Strain gauges and microsensors monitor every fraction of elongation. The data scrolls across computer screens in real time. Stress curves, displacement graphs, fatigue cycles. At first, the cable stretches slightly, the individual wires aligning under pressure. Then, and as the load increases, a low groan fills the air, the unmistakable sound of metal under extreme tension. For most materials, this would be the breaking point, but these cables hold fast, withstanding forces many times their own weight. Only when the test reaches the absolute design limit do technicians allow the cable to finally snap. The fracture point is analyzed under microscopes to examine how the internal structure behaved. Every failure is a lesson, every measurement a data point for refinement. In addition to tensile tests, other trials simulate real-world fatigue. Cables are bent thousands of times around pulleys, twisted under dynamic loads, and exposed to salt fog chambers that replicate decades of weathering. Only those that pass every test, dimensional, chemical, and mechanical, are cleared for certification. Step 17, certification and traceability. Each approved cable receives its own unique identity, a digital passport that records its entire life story. This isn't just bureaucracy, it's accountability on an industrial scale. Embedded within each coil's tag are QR codes and barcodes linked to a digital database. Scanning one reveals everything: the mine where the original iron ore came from, the chemical composition of its alloy, the batch number of the furnace it was melted in, every inspection result from diameter checks to tensile tests. This traceability ensures that years later, if a bridge inspector or engineer needs to know exactly what material holds their structure, the data is still available. Before shipment, the cables undergo final visual and dimensional inspections, often supervised by third-party quality assurance organizations. They issue certificates of compliance based on international standards, such as ISO 2408 and EN1 2385, guaranteeing that each cable meets or exceeds global performance benchmarks. The level of precision here borders on obsessive, but for an industry where human lives depend on every strand, there is no room for error. Step 18, packing and transport. Once certified, these massive coils, sometimes weighing over 50 tons, are prepared for transport. Watching the process is like observing a ballet performed by machines. Automated cranes glide silently overhead, attaching magnetic lifters to the coils. Step 19, real-world applications. Once installed, these cables become silent sentinels of human achievement. They hold up suspension bridges spanning rivers and harbors, raise tower cranes above city skylines, and lift elevators through the hearts of skyscrapers. In wind farms, they anchor turbine towers against roaring coastal winds. In offshore platforms, they tether structures to the ocean floor. Even in modern aerospace facilities, smaller versions of these cables are used in testing rigs and support systems. Each field has its own demands. Bridges need flexibility to endure temperature shifts and wind oscillations. Elevators demand consistent diameter and friction performance for decades of operation. Step 20, the legacy of steel. As the camera pans across the factory floor one last time, we see miles of shimmering cable coiled in perfect order, each one a product of human ingenuity and industrial mastery. From the raw ore pulled from the earth to the roaring furnaces, from microscopic inspections to global installations, every phase represents a link in a chain that holds modern civilization together. The real beauty of steel cables lies not just in their strength, but in their predictability. They are engineered to behave exactly as designed, to stretch within limits, to bear load consistently, to last for decades without complaint. Few people ever see the inside of a steel cable plant, yet their lives are supported by its output every single day. When they drive across a bridge, ride an elevator, or stand beneath a tower that scrapes the skin, each cable carries within it a story of transformation, of raw material turned into resilience, of craftsmanship merged with science. It's proof that progress isn't just about invention, it's about perfection. So the next time you look up at a suspension bridge or glide skyward in a glass elevator, remember the unseen giants holding it all together, forged in fire, tested in steel, and built to last a lifetime.